Great. So we are back in the last session, and let me admit right at the outset that I think I have not done justice either to reactive synthesis, nor will I be able to do justice to hardware verification. These are very vast subjects, but hopefully you'll get enough of an exposure, a taste, so as to be able to, you know, take this up further, and maybe figure out what might be appropriate for your specific context. So we went through this quick introduction to ROBDDs and AIGs, and now let's try to see some applications, some techniques that we can also perhaps use uh, in in hardware verification, that where whatever we studied earlier can be made use of. So the first problem that we want to look at is called combinational equivalence checking. So this is really saying that given two combinational designs, same number of inputs, same number of outputs, determine if each output of design one is functionally equivalent to the corresponding output of design two. And where is this used? This can be used at actually different levels, at different stages in a typical hardware design flow. So typically the way any complex hardware is designed is that you start off with a higher level description, maybe in a hardware description language, then you compile it down to some intermediate description, and then maybe further lower, maybe logic equations, and then maybe gate level, and then transistor level, and all of that. So there are so the same design is basically going through transformation from one level of description to another level of description. And what we would like to make sure is that as we are doing this jump from one level to the other level, the functionality of the design has not changed. So for example, I have said here that design one could be a set of logic equations, design two could be a gate level circuit, or design one and design two could both be gate level circuits. Maybe one is before a certain kind of optimization, the other is after that optimization. Or design one could be, uh, you know, a circuit in which there was maybe some redundancy, and in design two could be the circuit after that redundancy has been removed, or maybe some redundancy has been added. So there are different kinds of transformations that uh, a design can go through in the overall flow of a hardware design. And what we would like to make sure is that functionality that we don't want to change as it goes from uh, one stage to the other stage, uh, they are actually preserved. Okay, so here is a very simple way of looking at it. One could say that, well, ROBDD is a canonical function representation, so we can just construct the ROBDDs for each of the outputs and check. Now, this is okay in principle, but I guess, if your design blocks are large enough, then there is a little bit of a problem, in the sense that your ROBDD may blow up. Okay, so what one could do is one could construct AIGs and check for functional equivalence of the corresponding AIG nodes. And then there is also something called a MITRE-based approach, which basically converts this entire problem. So these are two designs, and here I have shown each design having two outputs, but they could have any number of outputs. And so you take these two designs and you create a new circuit out of it, right? Where the corresponding inputs are shared and the corresponding outputs are fed to XOR gates, and then you OR up the outputs of these XOR gates, right? So if you think about it, uh, if the two designs are equivalent at all of their outputs, then no matter what input you give here, the corresponding outputs will be the same, and therefore the output of the XOR gate will be 0, and so this output of the OR gate will be 0. So if the two designs are indeed equivalent, then this F should always be 0 for every input that you can give over here. On the other hand, if the two designs are not equivalent and there is some input combination here that makes a particular pair of corresponding outputs differ, So one of them will be 0, the other will be 1, and so the output of the XOR gate will be 1, and therefore the output of the OR gate will be 1. Right? So we can say the designs are functionally equivalent if and only if F is unsatisfiable. And of course, if you could do this using BDDs, then by the time you have constructed the BDD for F, you can already see, because there's only one canonical representation for the unsatisfiable function. But if you're unable to do it with BDDs, you can construct the AIG, and then we have seen site and transformation. We can just ask whether the resulting output function F is unsatisfiable or satisfiable. So this is one simple way of sort of taking care of arbitrarily many outputs by just adding these few extra gates and then just calling one SAT check rather than as many SAT checks as there are number of outputs. Now this is certainly in principle this should work if your SAT solver can building the AIGs is typically not a problem, because their size is kind of linear in the sizes of these designs. But typically what would also happen is that so in these two designs, maybe not everything has changed. Maybe there are large parts of the design that are still the same, and there are some parts that have been changed maybe. So when you're constructing the AIG, it is perfectly possible that nodes representing AIG nodes representing the functionality of intermediate circuit gates here and intermediate circuit gates here, they may get collapsed because of strashing, fragging maybe, right? So the final AIG that you create out of this may not be twice the size of the AIG for a single design, because it depends on how much part of the circuit was the same and how much of that could be caught using rewrite rules and strashing and fragging. And you might actually see that a large part of the circuit is shared, and then there are of course some parts of the circuit which are different, and then you want to do the equivalence check over here. You want to check whether F is identically 0, right? So this just says that in the process of constructing these AIGs, you may actually end up showing that two internal nodes in these two designs are still equivalent. Okay, and if that happens, there's actually a very interesting optimization that can be done. I'm not sure if yeah. So right. So the ROBDD solution, of course, is very elegant, but it is less scalable. The AIG-based solution is more scalable. And, as I said, if, for example, you have been able to figure out that there are intermediate points in this design which are equivalent to corresponding intermediate points in the design, because in the process of constructing the AIG, the corresponding nodes have been merged, then you can actually throw out the circuit prior to those intermediate points. It's effectively like having a cut here in this design and a corresponding cut here in this design, and you know that the things prior to the cut are all equivalent because the AIG nodes themselves have gotten merged, or whatever you have identified their equivalent by fragging or something. And so then the rest of the design that you have to then prove correct is actually could be smaller than the actual design that you're trying to prove correct. Okay, did this make sense? So as you're trying to build the AIG for this and the AIG for this, AIG nodes can start getting merged. And if AIG nodes are getting merged, it means the corresponding things are already equivalent. So if an AIG node arising from this design merges with an AIG node arising from this design, it means that merges with the corresponding AIG node from this design, it means that the corresponding points in the design were implementing the same functionality. And so you can then say that, well, if I can make a cut here, and if the corresponding points of the cut are already shown to be equivalent, then I don't need to, worry about what is the functionality of those of the outputs of the gates at the cut. I can just worry about the design later on. So I will, time permitting, I will show you one example of how this can actually simplify what the equivalence check can be, right? But the worst case complexity of this is necessarily bad, because we are trying to check unsatisfiability of, we are trying to check equivalence of functions. And there's no escaping the hardness of that problem. Okay. Now, at a very high level, if you agree with that as combinational equivalence checking, there's a very simple extension of that to what is called sequential equivalence checking. So in sequential equivalence checking, we are given two finite state machines, we are given two sequential machines, and we are given, in the simplest case, we are also given the correspondence between their state variables, and we want to know whether these two sequential machines are equivalent, in the sense that do they have the same sequential behavior. But if you know that the corresponding state variables are the same, I mean, if that equivalence between corresponding state variables is given, then really all you need to do is to check the equivalence of these combinational logic, right? The next state logic and the output logic. So this actually reduces to combinational equivalence checking if the equivalence between the state variables is given. Now, in general, the equivalence between state variables may not be given, or it may be, you may have to spend extra effort to try to find out if there is an equivalence between the corresponding state variables. So in general, the sequential equivalence checking problem is much harder than the combinational equivalence checking problem. But in the special case where the equivalence between corresponding state variables are given, it reduces to the combinational equivalence problem. Now, what do we do in general for the sequential equivalence checking problem? We will see if we have time, then we can, for example, the tool that we will use actually can do sequential equivalence checking, but we will see if we have time for that. Okay. So, okay. And, I think ABC is what we're going to see. Actually, there are several commercial equivalence checkers also in the market. And, typically a lot of heuristics would be used, but divide and conquer is usually, quite effective. Basically, if you can show that small parts of the circuit or small parts of the behavior are equivalent, then you can use that to show that other subsequent things are equivalent. Circuit structure is also used. For example, Wallace tree multipliers, Manchester carry adders, these can be pattern matched, and then you already know what they're doing. So all of these things can be used. Okay. Now, what I want to do is I want to talk about another technique which is quite powerful, which actually allows us to reason about sequential behavior. And for this, I will just switch to a different presentation. Just a second. So this new technique that we will talk about is really to reason about sequential behavior of circuits. And one might say that sequential equivalence checking is really one extreme case of reasoning about sequential behavior, because there we are trying to check whether two sequential circuits had exactly the same, to check whether two finite state machine implementations have exactly the same behavior, exactly the same sequential behavior, which means they have exactly the same state transition diagram. That's kind of a hard problem. I mean, that's also sometimes needed. But typically what we would do is we would say that, okay, there are some, properties of the sequential machine that maybe we care about. And even after, some change has been done, or maybe some extra functionality has been added to a design, we would like to make sure that the sequential properties are, still satisfied, right? And the technique we'll use for this is called model checking. And as I said, that typically when you go to complex hardware software systems, uh, it's kind of difficult to sort of establish that their behaviors are really exactly identical. But what we can hope to show is that the system satisfies a certain formal property as it is being optimized or as it's being transformed, considering all input cases. So specifically, what we're going to talk about here is a large class of practical hardware systems. So for example, things like this, a bus controller, and then maybe several peripherals on a bus. Uh, Systems that can be modeled as finite state transition systems, perhaps very large finite state transition systems, maybe a large number of variables in them. And the property that we would like to express about their sequential behavior is a temporal logic formula. Okay. And we want to now ask, in the synthesis question, we were given a temporal logic formula saying this is the property we want between the inputs and outputs, and synthesize a system that you know satisfies the specification. Here we are already given a system, which is the design, and we are given a property, and we would like to check whether the system satisfies the property. So our goal here is not to synthesize, but to check. Okay, and the technique that is used for this is also called model checking. Really check whether the system is a model of the given property that is expressed as a formula. Okay, so this is just to sort of give you a slightly high level idea of what's going on. So typically we would have multiple components. So for example, in this case, there are 3 peripherals, 1 arbiter, and there'll be all kinds of, there might be a fixed arbitration scheme. Each of the peripherals may have an application controller and a bus interface controller. We might say that the delays in the bus are negligible compared to, whatever the delays that we care about. So there are all kinds of these descriptions that will come for a typical hardware system that is given to you. And we want to reason about, so for example, here we might want to say that only one peripheral can be mastered at a time, or a peripheral requesting to be mastered eventually becomes one, or if a peripheral is not a master, then it should not be trying to take control of the bus, or should not be trying to place data on the bus, and so on and so forth, right? So we want to verify properties like these, which are at a slightly higher level, right? But it is not that they are kind of, if you look at this whole thing as a system, it is not that we don't care about what's happening in the internals of the system. We do care about things like this, that only one peripheral can be mastered at a time. Maybe that doesn't show up externally with, if this is part of a, maybe this is, part of a, whatever, maybe some controller in some automated, in some robot or something. So whether a peripheral is gaining control over the bus while some other peripheral is already the master of the bus, this may not show up at the external interface of the robot. This may be completely internal to the robot. But when we talk about verification of the hardware, where multiple components are interacting, we are perfectly free to talk about, signals. We're perfectly free to talk about variables on which we want to express some property, right? So this is just to say that this is a bit different from the synthesis problem. Synthesis problem is just input output, and then you synthesize the system. You don't care what happens in the internals of the system. Here, we can specify properties based on the internals of the system. Of course, when I say internal of the system, it is in the environment for the peripheral or in the environment of the arbiter, but it's still internal to the overall system where all of these are parts of. And we would like to sort of answer questions about that. Given a finite state transition model of a system, given a temporal logic formula which specifies some desired interaction between perhaps internal components of the system, maybe with the environment of the system, does M satisfy phi? Right? Is M a model of phi? That's why it's called model checking. And if the answer is yes, then we know that the system model exhibits the specified property. If the answer is no, then we typically get a counterexample trace, which actually demonstrates how the system can be forced to violate the property. So in order to do this, there are three essential components, as you might imagine. There is, we have to model the system, we have to write the property correctly in a mathematically precise way, and we need an automatic decision procedure to check if the model satisfies the property. And of course, if it does not, then we would like a counterexample to be generated. And of course, all of this, we would like it to be as efficient in practice as is possible. So when we talk about modeling system behavior, so, I might have maybe this is the bus controller over there, some simplified view of the bus controller. So which has some flip-flops, it is being clocked by, a clock signal, it has some gates, and then, things are getting fed back. Maybe some of these are going out of this controller, whatever. This might be my system. Now you could describe the behavior of this. So what does it mean to talk about, that the behavior of the system satisfies some particular property? So the behavior of the system can really be at multiple levels. For example, if I'm looking at the analog voltage at the output of these gates and all of that, my behavior might look something like this. And so do we want to reason about this? I mean, do we want our properties to be at this level? I mean, there is verification technology that can actually talk about continuous valued signals. And if you really want your property to be at that level, then you have to model the system at this low abstraction level. But this system could also be representing a state transition system like this, where I'm not really interested in the exact waveforms appearing on the outputs of different gates and so on. But I'm just interested in this high level abstraction about these are the values of the three flip-flops, 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. And I might be interested in the behavior at this higher level of abstraction. So what is very important when you're trying to model system behavior for verification purposes is that the same system can be described at multiple levels of abstraction. So you have to choose the behavior at the right abstraction level so that, it is suitable for the kind of property you want to check. I mean, if you really wanted to check whether there are overshoots, undershoots happening in these waveforms, then of course you have to model it at this level. But if you really wanted to check whether this is implementing a cycle of 8 states, then maybe it's okay to model it at this level. So the choice of the right level of abstraction is important. And that depends on what property you want to prove or what property you want to check. And whatever property is relevant. So for example, if your property is this, that when C is at 0.5 volt, clock can't be at 1 volt, then of course you have to model things like this. And indeed, there are verification technologies which will allow you to do this. But if you want to have a property like this, that ABC have a logic, that each of A, B, and C have the logic 1 value infinitely often, then perhaps, it's okay to model it at this level. So the right level of modeling is important. And how does it affect? So, modeling at a very low level means you have a lot of details of the physical behavior, but then you're going to pay a price in terms of how computationally difficult it is going to be analyze the model. Whereas as you go to higher levels of abstraction, you are losing details of the physical behavior, you're keeping more and more abstract behavior, and it becomes easier to analyze the system. Needless to say that this means that you can analyze larger systems, whereas this can only be done for smaller systems. There is one more thing that I think we must absolutely keep in mind when we are talking about verification of hardware, software, firmware, anything, is that at the end of the day, we verify that a model satisfies a property. Now, a model is not the same as the original system. A model is just a mathematical abstraction of the original system's behavior. So if a model satisfies a given property, we can say that the system would also satisfy the property only if the modeling was correct. Okay. If the modeling was not done correctly, or if the modeling was not at the right abstraction level, you can get wrong conclusions. So therefore, choosing the level of abstraction is very important. Now, why I'm saying all of this is because I will only talk about, modeling and reasoning at, at a very high abstraction level, where things are just zeros and ones. And, while there are powerful techniques to do that, but indeed there can be a need for verifying properties like what I showed you earlier. And in such cases, you have to use different kinds of techniques. I will not be talking about those techniques today. Okay, so this is just to show that there are actually several formal modeling languages available out there, uh, and you know these are basically these modeling languages have all kinds of features. They allow you to represent high-level data types, non-determinism, concurrency, communication, all kinds of things. So for our purposes, just to keep the discussion simple, given the time constraints, we will focus on the simplest formalisms. So what we will do is we will treat hardware blocks as reactive systems. We've already talked about reactive systems yesterday. So there's a continuous interaction with the environment, and these are different from transformational systems or functional systems, which just given an input generates an output and stops. So we will model these using finite state machines, and the states here are determined by values of latches and flip-flops. So of course, any hardware will have a finite number of latches and flip-flops. So the state space is finite, but it can be very, very large, right? I mean, if you think of the total number of flip-flops that are there in a modern microprocessor, that easily goes into several thousands, perhaps tens of thousands. And so the total number of states is 2 raised to number of that, and that can be very, very large. So we need to sort of use the right abstractions. We need to talk about, do we really care about the values of all of those flip-flops or not? And that's important. Now, given a state transition graph like this, so let us say that this is our finite state machine state transition graph. One could, I mean, for example, when we talked about LTL, we said that we're going to look at infinite runs coming out from this, right? If this is my milli machine, let us say, then I'm going to look at infinite runs coming out of this. And each such run is an infinite sequence, and there can be many such sequences. There is an alternative way to view the computation that is represented by such a state transition graph, and that is called an infinite computation tree, right? So in this particular case, for example, I will start at this state, and after that I could either go to the green or the yellow state, and from the yellow state I could either go to the red oval or the green state, and so on and so forth, right? Now, this infinite computation tree is one way of viewing the behavior of the system. Another way of viewing the behavior of the system is the set of all possible runs of the system. And this is what we have looked at during synthesis by saying that, okay, this is going to give rise to infinite sequences, set of infinite runs. Now, both of these are actually perfectly legitimate ways of looking at, what the system is doing, what the behavior of the system is. It's just that if you want to view the system as representing an infinite computation tree, then you need a logic to reason about trees. And if you want to view the system as a set of infinite runs, then you need a logic like LTL, which can talk about an infinite sequence of things, right? Here, this is not really an infinite sequence, this is an infinite tree. And we have already studied about LTL, which talks about infinite sequences. So what we are going to do in this thing is we are actually going to talk about another logic, which we'll see. So there are two kinds of temporal logics. One is this linear temporal logic, which considers evolution of time as a linear sequence, and then there's a branching time logic, which considers the evolution of time as a tree of events, and that's exactly what we did. And so LTL is linear temporal logic that we have already considered. Now, I want to briefly introduce this other logic, computation tree logic. And the reason I want to introduce this is because given the time limitations, it will be easier to explain to you how to check CTL properties than to explain how to check LTL properties, okay, on a given for a given finite state transition system. So I will just focus on CTL for simplicity. Okay. So CTL stands for computation tree logic, just 2 or 3 slides, not more than that, just so that we understand the language. So my hardware system represents some state transition graph like this. Of course, we don't have the state transition graph explicitly with us because, as I said, if a system has a few thousand flip-flops, the state transition graph probably has 2 raised to a few thousand states. So we cannot represent it explicitly. But conceptually, there is a state transition graph for the system. And so conceptually, if I were to unwind the state transition graph in this manner, I would get an infinite computation tree. Okay, the branching structure comes because maybe from the same state you can go either here or there depending on different conditions, or if you're working at a sufficiently high level of abstraction, maybe you don't even want to talk about the conditions in which you can say that I can go here or here non-deterministically. Okay. Now, CTL is not the only branching time logic that is there. There are other logics like CTL star and mu calculus and all of that. But we will just talk about CTL because that's the simplest one. Okay. So here is, I think the animation for this is a bit messed up, but okay, let's I don't think it will allow me to mark here. Okay, so CTL, it's like LTL. We have atomic propositions, which are basically values of variables, right? So it could be saying that some input is low, some output is high, some input is low, or some output is high. So these kinds of things. So atomic propositions are just the values of variables, and these variables by themselves, they can be true or false, and therefore they represent atomic propositions. And then we say that, well, so all of the atomic propositions are by themselves CTL formula. And then we say that, well, if I have 2 CTL formula, then I can, of course, combine them using the Boolean connectives, and I get a CTL formula. And then, if you look at this, this is kind of like what we have already discussed in LTL, the G operator, the F operator, the until operator, the X operator. But there's this extra part over here, which is this A and E. And you can think of it as saying all paths or exists a path. Right? This G and F and U and X, we can evaluate on one infinite path because that's how LTL was defined. But here we are kind of saying that, along all paths, phi always holds. In all paths and in all states, phi holds. Right? So it's something like this, that in all the states along all the paths, phi holds. EG would mean that there exists a path such that along that phi always holds. So I think this animation is broken a little bit, but suppose you had phi holding only along this state, this state, this state, and so on. So there exists a path along which phi holds globally. Phi may not be holding at the other states along these paths. So then we will say that EG phi holds, because starting from the root, there exists a path where phi holds globally. Similarly, AF would mean that in all the paths, finally phi holds. So, maybe phi holds here, here, and here. So in all the paths, finally phi holds, right? EF phi would mean there exists a path in which finally phi holds. A phi until psi means along all the paths, phi holds until psi holds. Similarly, E phi until psi. AX phi means along all the paths in the next state, phi holds. And EX phi means there exists a path so that along that path in the next state, phi holds, right? So these are, as you can see, that we are really using the temporal operators that we introduced for LTL. But here we are, since we're talking about a tree, so we will have to say whether we're talking about all the paths starting from a state, or we're talking about some paths starting from a state. So there is a path quantifier A or E that is prepended to it. Okay. Now I can, given this, I can actually talk about the truth or falsity of a formula at any given state, right? For example, AG phi would mean, if I want to evaluate AG phi at this state, it means for all the paths starting from this state, does phi globally hold? So in which case I'm not interested in the paths here, because those paths are not starting from this state, right? So I can, position myself at any state, and I can ask whether a particular formula hold by looking at the infinite tree rooted at that state. Remember, this whole thing is an infinite computation tree. So no matter where you position yourself, you'll see an infinite tree going out from there. And you answer the question whether the property holds for that infinite tree going out from there. Okay, so here are some quick examples, simple examples. So for example, maybe this is a traffic light controller. So I want to say, along all paths, it should always hold that there is a side road turning green and highway turning green. Both of these should not simultaneously be true, right? Basically saying that no matter which way the system evolves along all the paths, it should always be the case that the green signal should not turn on the side road and the highway at the same time, right? So this is saying that along all paths, it should always be the case that if there's a car waiting on the side road, then the side road should eventually turn green, right? So if in any state you see a car waiting on the side road, then starting from that state and all the paths going out from that state, finally you should be able to see a side road green. Okay. So the last one is saying request implies EF grant, which means that if in a state you have made a request, basically this is saying if in the starting state you have made a request, then there should exist a path going out from the starting state in which eventually grant becomes high. There's at least one execution such that a request made is granted. Of course, if I write the formula like this is only talking about the starting state. If I want to put AG around it, then it will mean that in all the states, along all paths in all the states, this property should hold, that if I make a request, then eventually along some path from that state, the grant will become high. Okay. So are these examples clear? I mean, this is, I'm just trying to illustrate some simple examples of CTL, but do these examples make sense? The operators, I mean, the G, F, X, and U, you already know. There is just a path quantifier before it because we're talking about trees. So you can talk about all paths going out from a state, or you can talk about some paths going out from a state. Okay. Are there any doubts about this? Okay, I don't know how to interpret that silence, but hopefully things are fine. Let's see. Okay. So given a finite state transition system, forget about this name, M, and a CTL formula phi, we have seen some examples of CTL formulas. It turns out that there is actually an efficient algorithm to check if this finite state transition system satisfies phi. Now, why do I say this is efficient? Because you see, this is linear in the size of the transition system and in the size of the formula. Now, does this really mean efficient in practice? Remember, if in a hardware system, if you have n flip-flops, then that system has 2 raised to n states, right? So this M is the size of the state transition system. So this is 2 raised to n, where n is the number of flip-flops, and of course, it's the size of the formula. So it's not really efficient in the number of flip-flops or in the size of the circuit that you're trying to check for the property, but it is efficient in terms of the size of the transition system. And in fact, this will be a primary problem that we would like to solve, because I mean, we don't care about the size of the transition system when we are designing circuits, right? I mean, I have a circuit. If that circuit has 100 flip-flops, for me, maybe it's a small enough circuit. and I would like to test some properties on that circuit. It's a completely different matter that the state space of the circuit is 2 raised to 100, because I never need to represent that 2 raised to 100 states transition diagram when I'm trying to design that circuit. So really what we would like to do is to say that, okay, if you give me a circuit, and if that circuit is of manageable size, then can I check this? Does the state transition system represented by that circuit satisfy the given formula? Okay. So towards that end, what we will do is we'll first see, okay, how we should do this if we actually had access to the state transition system, right? We'll consider some very toy small state transition systems, and we'll see how we might want to do it. And then we will see that when we really don't have access to the state transition system, but just the circuit, then how do we do it? Okay, so let's consider a simple example where we have access to the state transition system, and let's say this is how it looks like, and this is the initial state. What these mean is that, these are things like, some input output variables maybe. So there are two variables here. In this state, this is, both of them are low. In this state, one is high, the other is low, and in this state it is flipped. And this is how they move around, how the state transitions happen. Now, I am interested in knowing that in which of the following states. So note that currently I'm given a state transition system. In reality, I will not be given a state transition system, but I'll be given a circuit whose state transition system will be my object of interest. But even given the state transition system, there is actually, this state transition system represents an infinite tree. And these formulas are talking about paths in that infinite tree. So how do I reason about that infinite tree from this state transition system? And then at the next step, how do I reason about those infinite tree from the circuit whose state transition diagram is the state transition system? Okay? So let's first try to understand how would I be able to figure out that, if EFP is my formula of interest, or EGP, how would I figure out which state here would satisfy EFP or which state here would satisfy EGP, which means the infinite. So as if I unfold the computations represented by this finite state transition diagram as an infinite computation tree, then for the infinite tree rooted at which state, for the infinite subtree rooted at which state would these formulas be true? That there will be an infinite path in that infinite tree rooted at that state of interest, such that eventually P is true there, or globally P is true there, or Q is true until P is true, and so on. Okay. So the way this is done, the way we actually do this, for the time being, we have access to this explicitly drawn out state transition diagram, is we are actually going to do an iterative labeling algorithm that will label the states with the subformula. Okay. So I'll just show you how to do this. So, what are the subformulae here? So, if I'm trying to talk about EFP, it means that there exists a path starting from the current state such that P is eventually true along that path. So when would P be eventually true along that path? If P was true right at the state of interest, or if P was, if there was a path such that along it, in the next step, P was true, or if there was a path such that along it, 2 steps down the line, P was true, and so on, right? Basically, this is saying there is a path such that 1 step down the line, the state that I reach satisfies EXP, which means 1 step down the line, if I start drawing the path from that state, then 1 further step away, there is a P, right? So I can keep doing this, and of course, this will go on forever because we're talking about an infinite tree. What does EGP mean? It means that there is a path such that P is true all along that path, which means P is true in the current state, P is true in the next state, P is true 2 states down the line, and so on. What does EQ until P means? Once again, there is either P is true in the current state, or Q is true in the current state, and there is a path such that P is true down the line along it. So it could be true down the line 1 step away, or it could be true down the line 2 steps away, but then 1 step away Q should have been true. So this is really representing what we mean by Q until P being true, that either P is true now, or Q is true now and P is true next, or Q is true for the 2 steps and P is true in the 3rd step, and so on. And of course, I've put dots here. So really, these are not formulae because these have to be written down ad infinitum. But this is just to get the intuition that this is really what is happening. This is when I would say a state satisfies EFP if it satisfies any one of these formulas. I would say a state satisfies EGP if it satisfies all of these formulas. Right? So we will actually come up with an iterative labeling algorithm, which will try to label the states with what formulas are true in that state. And this algorithm starts with labeling the states with their initial labels, which are the atomic propositions, which is like what we had over here. Right? We know what variables are true or false in what state. And then we will iteratively add some formulas based on these equations. Okay. So let's see. So suppose I want to, suppose I have a state transition diagram like this, and I want to figure out which states will satisfy EFP. So I say, okay, EFP means this, either P is true now or P is true one step down the line, or one step down the line, I can see some state where one step down the line P is true, and so on. So first I'll mark the state which has P in it, which already has P in it. That definitely satisfies EFP. Okay. Then I'll say that, well, all states which can reach this marked state in one step, they also satisfy EFP, because, if in one step I can reach that satisfies EFP. And then in one step, if I can reach a state which already satisfies EXP, then that will also be marked EFP, right? So I'll basically continue this. So this state is marked, then I do a backward reachability. I say, okay, now that state should be marked, and then that state should be marked. After that, is any state going to be marked? I have to see that are there any other states such that from there you can reach any of these states you have. But unfortunately, there are no other states. And so this iteration now terminates. And the marked set of states that you have are really the states from where EFP holds. Remember, P was true here, nowhere else. And indeed, from here, you can find a path where P holds. From here, you can find a path where P holds. And of course, this one, P holds. But from this state, you cannot find a path where P holds. And since there are finitely many states in the state transition system, so we know that this process must stop at some time. At every step, either you're marking, shading a new state, or you have already stopped. There are no new states to be there. So, so the computation really involved a backward traversal and calculation of strongly connected cycles. What about EGP? Right? So let us say I have this state transition diagram, and I want to know which states will satisfy EGP, which means which are the states such that starting from there, I will be able to find a path, exists a path, such that along that path P always holds. So I will start by saying, okay, this is how EGP looks like. EGP means it should be true in that state, P should be true in that state. There should be one state away from it where P should be true. Should be two states away from it where P should be true, and so on. So I'll start by saying, okay, let's find out all states where P is true. Actually, yeah, I mean, this is going one step even further, saying that let's start with all the states, and then in the first iteration, we finally find the states where P is true. Okay. And now we have to say that, well, it also has to be the case that one step later, I should be able to see one of these shaded states. Now, for which among these states, one step later, can you also see one of these shaded states? Not for this, right? Because one step later, you can't see a shaded state. But for this and this, you can see one step later a shaded state. So you say, okay, this must now become unshaded, but these two can remain shaded. And then you ask the same question, that now one step later, when can I see a shaded state? This again goes out, and only this remains. So that is finally the state which satisfies EGP. Indeed, there is a path starting from this state which satisfies, on which P always holds. There is another path starting from that state on which P does not hold, but that's okay because we were talking about EGP. Okay. So once again, the algorithm involves backward traversal, and as you can see, it's kind of linear. I mean, at every step, either the state of shading is changing, or the state of shading has already become static and it won't change any further. So it involves a backward traversal, and it's linear in the sizes of both the formula and the model. But the size of the model is exponential in the number of latches or flip-flops. And so using this technique, maybe we can verify small size systems, but not large size systems. I mean, we can't write down state transition diagram with 2 raised to 100 states and then do all of this, right? Even if there are a modest number of latches or flip-flops like 100. So what do we do in such cases? So we ask that, well, can we avoid representing the state transition system explicitly? Can we represent it symbolically? Can we encode it in logic? And then not only that, we would like this backward traversal that is happening to happen on that symbolic representation. Okay. So by the way, I sort of showed you only these 3 kinds of formulas here: EF, EG, and EQ. The other formulas, when you have A, can be reduced to E, right? Because you have seen this in your lesson on first order logic, that if I say that along all paths something should hold, then it means that it is not the case that there exists a path on which that thing does not hold, right? So for all X, something is the same as negation, there exists X, negation that thing, right? For all X phi is the same as negation exists X, negation phi. So that is why it's sufficient to talk about the existential quantifier on the paths here, because if you give me, for example, if you give me a formula AFP to check, I will say, okay, you want to know whether along all the paths FP holds. This is the same as saying, this is, so if I negate this formula, I will get E negation FP. And what is, right? Basically, I'm saying, does there exist a path such that finally along it negation P holds, right? If you want me to check whether AFP holds, it means along all the paths finally P should hold. If I consider the negation of this formula, then negation AFP is E of negation FP, right? Does there exist a path such that along it, it is not the case that FP finally holds, but then we have seen how to push the negation inside the temporal operators. So E of negation FP will become E of G negation P, and that falls in this format. So therefore, we can find it out, right? And remember, this is actually the process that we talked about. It's actually telling us all the states on which a given formula is true. So the states that are not marked finally are the states on which the given formula is false. The states on which the formula is true are shaded. The states on which the formula is false are not shaded. So by repeating this process, I can find out, if you wanted me to find out where AFP is true, I'll really do EG negation P. And whatever states are not marked with EG negation P, I know that AFP would be true there, because negation of AFP is EG negation P. Okay. So that is why it's sufficient to use these E formulas, and that's just this backward traversing. Okay. So we want to talk about this, symbolic way of doing this model checking, symbolic way of checking these properties, and the method that I just showed you is called explicit state model checking. And the method that we want to talk about now is called symbolic model checking. So here we are going to not represent the state transition graph explicitly. We are going to represent state transitions and sets of states implicitly. And for this purpose, we will use Boolean formulas, which we will be representing using BDDs and AIGs. And we will see that, some of the operations that we have seen earlier can be used to basically do this search, this backward search on this implicitly represented state transition graph. We don't want to represent it explicitly. We want to just use the circuit, the finite state machine circuit, to represent the state transition graph. And this scales well to maybe a few hundred flip-flops, but it has problems even beyond that. And I'll tell you briefly about what we do when we go even beyond that. And once again, there are fairly mature tools that exist. Okay, so BDDs we have already seen. So how do we do this symbolic, checking of CTL formulas? So here is our favorite circuit, and this has a state space of size 8. But what I want to do is, I don't want to represent that state space explicitly. I want to represent this circuit. So basically, I want to say that what is the next value of x0 from the current values of x0, x1, x2? I want to write out the next state, the state transition equation, so to say. The next value of x0 is not of the current value of x0. The next value of x1 is XOR of the current value of x1 and the current value of x0. The next value of x2 is XOR of the current value of x2 and the AND of the values of x0 and x1, right? So if I have n flip-flops, I need to write down n equations here or n Boolean functions here, and that represents this entire circuit, and this circuit represents the entire state transition system with 2 raised to n states, right? If a circuit has n flip-flops, the state transition diagram of this has 2 raised to n states in the worst case. So I am now representing a state transition diagram with 2 raised to n states by using n Boolean functions. Okay, and that is the symbolic representation. I'm not going to represent that explicitly because I cannot. When n becomes large, I cannot represent it explicitly. So I'm going to represent it using these n Boolean functions. And then maybe the property that I want to check is this state 1, 1, 1 reached infinitely often starting from 0, 0, 0 along all paths starting from 0, 0, 0, right? So, what we're going to do is that we are actually going to, you saw that we really need to do this backward traversal to figure out which states satisfy the formula. So we are really going to, so this backward traversal can also be thought of as reachability analysis. We are trying to find out all states reachable from a given set of states. And we'll try to see, which of these states are going to satisfy some property and which are not going to. So here is how it works, okay? So for a 3-bit counter, which is the circuit that we looked at, the set of states are the valuations of the 3 flip-flops, right? And this can be represented by a formula on those 3 variables. So whatever valuation of the variables causes this formula to evaluate to true, that valuation of the corresponding state, that the state corresponding to that valuation of the variables is said to be in the set S. So I'm representing a set of states by a formula on the variables where each state is a valuation of all these 3 variables. Okay? So this is an important idea to note, is that, for example, if I say x0 prime, then it represents all valuations where x0 is 0 and x1 and x2 can be anything. So these are the 4 valuations where x0 is 0 and x1 and x2 can be anything. So this formula x0 prime represents this set of states consisting of 4 states. And I can represent this formula x0 prime, of course, as an AIG or as a BDD. And what you see immediately is that the formula representing a set of states can actually be much, much more succinct, can be much smaller than the size of that set of states. And this is what we wanted to do, because our, the total number of states is very large. So the sizes of the sets of states will also be large. We don't want to represent them explicitly. We want to represent them using small compact formulas, which can be represented using BDDs or AIGs. Similarly, the state transitions can be represented by state transitions between states, each of which has a valuation of the 3 variables x0, x1, x2. So state transitions can be represented by a formula on 6 variables, where the first 3 variables refer to the state from which the transition is happening, and the next 3 variables refer to the state to which the transition is happening, right? So for example, here, if I say that, this is really coming from these equations here, that in the next state, the value of x0 should be the not of the value of x0 in the current state. In the next state, the value of x1 should be XOR of the value of x1 and x0 in the current state. So that's what is written here, right? So I'm writing out a relation between the present state variables and the next state variables, and any valuation of the present and next state variables which satisfies this relation represents a state transition from the state represented by the smaller case letters, values of the smaller case letters, to the state represented by the values of the uppercase letters, right? So if you look at this formula is a formula on these 6 variables, and any satisfying assignment of this formula gives you values of these 6 variables which satisfies this formula. Now, if it satisfies this formula, it actually means it is satisfying the next state equations that we had written, which means from the values given by the lowercase letters, the state can actually transition to the values given by the uppercase letters. So this is once again another way in which you can represent a set of state transitions in this case. Earlier it was a set of states. Now you can representing a set of state transitions using a Boolean formula, and of course this formula you can now represent using a BDD or an AIG, for example. And then how do we do reachability using either BDD or AIG? So we say, okay, let's start from a set S0 of states. Remember, a set of states is going to be represented by a formula like what we had here, right? Like what we had here, a formula representing a set of states. So let's start from a set S0 of states, which is represented by a formula. And then let us try to compute the set of states that I can reach in one step starting from the set S0. So the set S0 are the black states. I want to find out the set of states that I can reach in at most one step starting from S0. And I want this new set of states S1 to be also represented as a formula, because I never want to talk about explicit sets of states, right? About sets of explicitly represented states. I always want to talk about formulas that are going to represent sets of states. So what is the formula that represents the set of states S1, which is, what is the definition of S1? The states reachable in at most one step from S0. So of course, whatever is in S0 can definitely be reached within one step from S1 and at most one step. So it is definitely the whole of S0 union all those states, all the capital X's, such that there exists a small x in S0. There exists a present state in X0. And the next state transition relation between that small x and that little x is 1. Whenever I have this, I can put that capital X, whatever value of capital X it would have, in the set of states that I can reach from S0 within one step. Is this clear? This step is very, very important. This is basically saying that all the states, in fact, these three white states, such that there exists some state little x which is in the set S0, and from that little x there is a transition to capital X. Remember, we had represented this by a formula, we had represented this by a formula. So I can actually now construct the formula for S1 saying, okay, S1 as a function of X0, X1, X2 is S0 as a function of X0, X1, X2. Union becomes OR, right? Whatever was there in S0, I want to be included. So whatever satisfies this S0 formula, I want it to also satisfy this one formula. So it is S0, X0, X1, X2, or this is just the same thing I'm writing in terms of formula, that X should be in S0, which means S0 should evaluate to true when I plug in X as its argument. The formula S0 should evaluate to true when I plug in X as its argument. Right? I mean, by S1 and S0 here, I mean the formulas that represent these sets of states. So since X should be in S0, it means that the formula S0 should evaluate to true when the values of lowercase x are substituted, are plugged in. And I want this to evaluate to true, which means I want, with the lowercase x and the uppercase x, this formula to evaluate to true. And, I don't want to talk about the specific little x. I just say that there exists some little x. There exists some black state from which I can come to this white state using this n transition relation, right? So I want to existentially quantify out these small x variables, right? So now if I give you BDDs or AIGs for S0 and n, then if I give you a BDD for n and if I give you a BDD for S0, we have seen how to construct the BDD for S0 and n. We have also seen how to construct the BDD for existentially quantifying out some variables. Existentially quantifying out a variable is really setting that variable to 0, setting that variable to 1, ORing it up, right? And we have also seen how to do this disjunction with another BDD or AIG, let us say. So given BDDs for S0 and n, we can compute the BDD for S1, for example. Okay. This is a very important step because we have not represented the set S0 of states explicitly. We have used a Boolean function in this case represented as a BDD to represent a set of states. We have not represented the transitions explicitly. We have used basically the next state transition equations of the finite state machine to represent the transition symbolically. And once I have these two, I can actually calculate this. And now I can repeat it. So from S0, if I can compute S1, from S1, I can compute S2, which is what is the set of states such that they are reachable in at most one step from S1. And S1 was itself reachable in at most one step from S0. So therefore, S2 are the set of states that are reachable in at most two steps from S0. Similarly, S3 from S2 means reachable in at least three steps from S0. So in general, if you have the function or the BDD representing Si, the number of the set of states, the BDD representing the Boolean function which encodes the set of states that are reachable in at most I steps from S0, we can find out Si plus 1 using this technique. I'll have to just substitute Si here, and I'll get Si plus 1. Right? So I should just continue to do this, basically getting Si plus 1 from Si using this transformation. So this is the transformation. This is what I mean by the function f. Given S0, I can get S1. So similarly, given S1, I can get S2, and so on. And finally, each time I compute this, I'm potentially looking at a larger and larger and larger set of states. Just doing exactly the reachability that we talked about. But because there are only finitely many states, we know that at some point of time, this has to stop. The set of states cannot keep increasing indefinitely, which means the Boolean function sk plus 1 at some point of time should become the same as sk. That is, I've found the set of states that's not expanding any further. Now, how do we check whether sk plus 1 has become the same as sk? So this is also called the least fixed point of this state transformer, the predicate transformer. But how do we check if sk plus 1 has become the same as sk? So every time I use si to compute si plus 1, I have to check whether these two are representing the same function or not. I mean, using BDDs, this is very simple. Just check whether the BDDs are isomorphic. Using AIGs, this is also not very hard. Just check whether the two functions, put a miter at the outputs of those two functions and check. Now, what this allows us, what this has given us is that now we are actually able to do reachability, but without talking about the states explicitly. So we can now represent very large sets of states compactly. We have already seen an example over here that just, one literal thing. I mean, just think about that if there were 100 state variables, x0 to x99 maybe, this formula x0 prime represents all of the valuations of the 100 variables in which x0 is false. So it really represents, 2 raised to 99 states. It represents a set of 2 raised to 99 states. So the size of the state set is very large, but the formula representing it can be very small. Okay. And that's all. I mean, that's what we have achieved through this technique. And, we did forward reachability here, starting from a set of states. We found out what are the next states. We can also do backwards reachability. We can start from a set of states and say, okay, what are the states that are going to reach this set of states, right? So this is exactly the same as the forward reachability case, except that when you talk about the next state transition relation, you don't say that I'm trying to go from this state to that state. You basically switch the roles of this, right? You say that I want to know the states from which I can reach this state, not the states that I can reach from the current state. Okay. So, and then, I mean, things like if I want to check whether my set of states, and remember, how we were doing the CTL model checking, how we were labeling the states earlier, we were basically just looking at, starting with a set of states, we were looking at what states can be reached from it or what states can reach it, as long as they satisfy a certain property. Basically, are they shaded? Can I reach a state which is shaded, or can the current state be reached from a state which is shaded, right? So this is really saying that if you determine, if you tell me a set Z of states, which is perhaps shaded or something, then I can tell you whether the set of which of the reachable states intersects with those shaded states, right? So the set of states of interest could be things that are violating some safety condition, could be things that we want to see whether we can reach those, could be any arbitrary set of states. And what we can do is we can compute the set of all reachable states using this technique that I just mentioned, right? Using this technique that I just mentioned. And then we can, and we'll get a formula that represents the set of all reachable states. If we have a formula that represents the set of states of interest, I can conjoin these two formulas and check if there is a common state between them, which means if these two sets intersect, or if they're disjoint, or if one is subsumed within the other, all of these can be done, right? So this is really saying that, starting from a set S0, I can move forward, find out the forward reachable set of states, and then see if Z is intersected here, or if Z is included here, or if Z includes this. All of these checks are now really, because the set R is represented by a formula, the set Z is represented by a formula. It just amounts to checking some relation between these two formulas. And similarly, I can do backwards reachability. Starting from a set Z, I can find out all the states that can eventually reach Z, and then I can check whether the initial set of states intersects that. Okay, so as we said, that it's sufficient to give algorithms for EG, EX, and EF until G, because all the other formulas can be represented like this. And each of these really amounts to doing either forward reachability or backward reachability and marking states as you're going. And this is exactly how we do it, right? We do forward reachability, backward reachability exactly like this. And then to figure out if this correspond to the marked states, we just look at the formula that represent the marked states and either intersect with it, or either take the AND with it or take the OR with it, depending on whether we want to add to the set of marked states or whether we want to subtract from the set of marked states. Okay, so I guess, I should stop here. But before I stop, I will just take, maybe another 3 minutes to talk about a few techniques that, this is the basic technique for doing symbolic property checking, which is really what we want to do when we are verifying properties about hardware. And, blow-ups can happen, we have seen. And then there are, different kinds of optimization techniques that people use to address these blowups. I think a few hundred, probably it even goes up to 500 these days, you can do with BDDs, but beyond that, you cannot do with BDDs. So what do we do when BDDs fail? So this is something called bounded model checking, and I'm just going to explain this very quickly. So this says that, well, your sequential circuit, your finite state machine looks something like this. These are the flip-flops. They provide the present state value. The inputs are coming here. The outputs are going there, and these are the next state values. And as this finite state machine keeps running, we are basically traversing the state space of the system. And we have just seen how to do a symbolic forward reachability or a backward reachability in the state space. But once again, if the BDDs are, sort of blowing up, or if the AIGs are blowing up, then there is a problem. And in particular, there is this operation here which can create problems, the existential quantification. This is known to cause blowups when you try to do this symbolic search. So what people have done is they have said, okay, let's not try to represent the set of states with formulas, but let us just take this circuit and let's just unfold it. Let's just unroll it effectively. So instead of sending the next state values back here like this, you send the next state values to another copy of the finite state machine circuit, and then the next state values to another copy of the finite state machine circuit. And of course, you say that the inputs that are coming to the first one are the ones that are to be paired up with the initial state. The inputs that are coming to the second one are to be paired up with the state that is generated and should have been fed back at the next time instant, and so on and so forth. Right? So of course, how long should you unfold it? It should be as large as the number of, maybe the largest cycle length in your state transition diagram, but that can be very, very large. That can be 2 raised to n. if there are n flip-flops. So we typically don't do it that way. We say that, okay, let's unfold it maybe 100 times or 300 times. And so we get one big circuit like this, right? Remember, each of these is a Boolean circuit. So we get one big circuit now, which has been unfolded maybe 300 times or 100 times. And then we want to ask if a state that is represented by a formula Z, remember formulas on state variables represent sets of states. So if a state in the set represented by the formula Z is reachable starting from the starting state within these first 300 iterations or within these first 100 steps. So the number of times I've unfolded it, that many number of steps. And in order to do this, I can construct a formula like this, which says, okay, does S0x, which means a state that is part of the initial set of state, is it also part of the set of states Z? Remember, these are formulas. So if a state satisfies this formula, it means it's in the set represented by that formula. So if the conjunction of these two formulas is satisfiable, it means I have a state which is in the set represented by S0 and also in the set represented by Z, which means I have a starting state which is in the set Z. So I say, okay, is this satisfiable, or is it the case that S0x and next xy, remember this was the transition relation, which is basically saying how does the next state, how is it expressed in terms of the present state and the present inputs. So S0x and the relation between the current state and the next state is, so the current state is the start state, this is the next state that I reach in one step from that, and then is that next state that I reach, is it part of the set represented by Z, or can I go 2 steps and is that part of the set represented by W, and so on. Okay, so this is one large formula, and of course I have, every time I did this unfolding, I had to introduce a separate copy of the state variables. I can't reuse the same copy. So there are k sets of state variables introduced, one set for each time step, and then I can form this one large formula. This formula may not be in CNF, but we have seen earlier today how to take an arbitrary Boolean formula represented by an arbitrary circuit and convert it to an equisatisfiable CNF formula, which is the cite and encoding. So we can just do that and feed it to a SAT solver, and the SAT solver will tell us a yes or a no. If it tells yes, this is satisfiable, it means that starting from a state within this initial set of states represented by S0, it is possible within k steps to reach a state that satisfies Z. Okay, so because SAT solvers have grown extremely powerful these days, so therefore this is actually a very viable technique. And you think about it, what this is doing is, if you have unfolded it 100 times, it is actually looking at all possible paths, because when I'm searching for a satisfying assignment, I'm perfectly free to use any x that satisfies S0, any y that satisfies n, any w that satisfies this n, and so on, as long as the relations between the x and the y and the w are specified by these formulas are satisfied. So if I have unfolded it 100 times, it means I'm looking at all possible executions of this FSM, starting from all possible states that are represented by this formula S0, and I'm checking whether any of those states that are reachable in 100 steps of execution from any of the starting states, does any of them lie in the set Z? This, although the depth of the search is limited by the 100 steps or whatever I have unrolled it, but the breadth of the search can be huge, right? The total number of states that I can reach in 100 steps can be in the billions. Okay, and when I feed this to a SAT solver, it actually tells me something about all those billion states, whether any one of those lies in the set Z or none of those lie in the set Z. So that's why this is an extremely powerful technique. Okay? And with that, I want to end by saying that this is one way in which SAT-based techniques have been used for bounded model checking. And of course, you can represent these formulas using AIGs and then convert them to CNF. There are other SAT-based, so this is called SAT-based bounded model checking because you're bounding the depth up to which you want to see. There is also something called SAT-based unbounded model checking, where you basically take the same, formulation that we use for BDDs, but then you actually use information from within SAT solvers, because when a SAT solver is trying to check satisfiability, it can often learn relations between different variables. You can infer relations between variables to identify invariants, right? That as you are doing a backward reachability, you're always going to lie within a certain set of states. And these can be used to obtain the symbolic image directly. And then, the latest set of techniques uses what is called interpolation. And interpolation is basically a very simple idea which says that if I have two formulas that are sharing some variables, right? So there is a formula psi and there's a formula phi, and they're sharing the variables y1 to ym. And if the conjunction of these two formulas is unsatisfiable, which means whenever this becomes true, this must become false, and whenever this becomes true, this must become false. So the two together cannot become satisfiable. Then it means that whenever you're setting this to true, there is something that is happening to these variables which is preventing, because that's the only way for these two to communicate with each other, right? Those are the only common variables. So whenever you're setting this to true, there is something that is happening to these variables which is preventing this from becoming true. And similarly, whenever you're setting this to true, there is something that's happening with these variables that's preventing this from becoming true. So basically, there exists a formula on these common variables such that whenever psi evaluates to true, this formula on the common variables evaluates to true, and that formula on the common variables prevents phi from satisfying. Okay, and this rho depends only on the common variables, and this rho is also called an interpolant between psi and phi if psi conjunction phi is unsatisfiable. And how is this used in model checking? For example, suppose I find out that starting from the starting set of states in one step, I cannot reach the errors, right? So maybe these are the set of states where there is some error. This is the set of states from where I'm starting, all represented using formulas. This is the transition represented using formula. So suppose I find out that starting from the starting states in one step, I cannot reach the error state, which means that this formula is unsatisfiable. Then what I can do is I can try to find an interpolant of this green part and the red part. And what is the common variable in the between part? It's only x prime. So I should be able to find a formula only on x prime such that the green part will imply that, and that along with the red part will become unsatisfiable. So what does this mean? That if you start from the starting set of states, and if you take one step, you are going to satisfy this formula on the next state variables. So this is an over approximation of the set of states that you can reach starting from S0 in one step, right? Starting from S0, if you take one step, you are going to satisfy this formula on just the next state variable. So this is an over approximation of the set of states that you can reach in one step. And this over approximation is safe in the sense that it doesn't intersect with the error states. So you can actually use these over approximations to speed up your search. So instead of using S1x, which would be exactly the set of states that you can reach in one step, you can use F1x, because since you have done an over approximation, but it's a safe over approximation, you can start from there and see what states you reach next, and you can do your reachability computation like that. So let me stop there.
Thank you, sir.
Thank you, sir.
Thank you, sir.